Section 4.4, Mean Value Theorem. Mean Value Theorem, abbreviated MVT, is important because it's used in the proofs of other theorems, including theorems we have been using to identify features of graphs and locate extreme values. We start with a special case of MVT called Rolle's theorem. Rolle's theorem says that if a function f is continuous on a closed interval AB and differentiable on the open interval AB, then, and if f of A is equal to f of B, then there's at least one number c on the open interval AB such that f prime of c is equal to 0. And the picture kind of illustrates this. We have f of A is right here, the point A, f of A, point B, f of B is right here. So the slope of the secant line connecting those 2 points is 0. And if x is continuous, at some point at some point on that interval, the slope of the tangent line also has to be parallel to that. It has to be horizontal or have slope 0. So it seems intuitively clear that it should be true, but it's important to prove it. And we'll do some examples and go over a proof. Okay, so the first example, f of x equal minus x squared plus 4x plus 1 on the closed interval 1 to 3. So this is a polynomial. It's continuous and differentiable everywhere. Polynomials are continuous and differentiable on minus infinity to infinity. So those are both checked off. F of b is f of 3. Minus 3 squared plus 4 times 3 plus 1, that's equal to 4. F of A is equal to minus 1 squared plus 4 times 1 plus 1, that's equal to 4. So that's also true. And then we just want to check that f prime of x is equal to 0 at some point on that interval. So f prime of x is minus 2x plus 4, and set that equal to 0. Solve for x. Subtract 4 from both sides. Minus 2x equal minus 4 divided by minus 2. We get x is equal to 2. So 2 is on the interval from 1 to 3, and derivative at that point is 0. So c is equal to 2, and the conclusion is satisfied. If the conditions are satisfied, then the conclusion is automatically satisfied. If it's not, then we're really going to rock the boat in the mathematical community. You have something that can be published, but it's been established and agreed upon, proven that the result should hold true. Example 2: f of x equal cube root of x squared on the interval minus 8 to 8. So this is we can write this as x to the 2/3 power, so this is continuous. The algebraic functions are continuous except where they're not defined. So this is continuous, but it's not differentiable when x is equal to 0. So f prime of x is going to be 2/3 x to the minus 1/3 using the power rule. So this is 2 over 3 cube root of x, and not differentiable when x is equal to 0. The derivative is undefined there. X is equal to 0. So the first condition is true, but the second condition is not. Let's see, the third condition, f of, well, this is an even function, so f of minus 8 should equal f of 8, but anyway, f of minus 8 cube root of minus 8 squared, negative squared is positive, cube root of 64 is 4. F of 8 cube root of 8 squared, cube root of 64 is 4. So f of A is equal to f of B. So that condition is satisfied. but the only one that's not satisfied is the differentiability. So we can also check the conclusion. If the three conditions are not satisfied, if any one of them are not satisfied, then the conclusion may or may not be true. So let's see if it's true. So f prime of c, well, solve f prime of c is equal to 0. So that means that 2 over 3 cube root of x equals 0. The only way that this could be equal to 0 is if the numerator is equal to 0. But that's a contradiction. 2 is not the same as 0, so the conclusion is not satisfied in this case. The graph of this function is going to look something like this. It's an even function, so the left side is the mirror image of the right side, but it'll look something like this. It'll have a cut at 0, where it has a steep slope, but it never reaches slope 0. It changes from negative slope to positive slope, but it doesn't hit all the points in between. Okay, so f of x equal x squared plus 1 over x squared on the interval from -2 to 2. It's another even function. So this is not continuous when x equals 0, not continuous, and if it's not continuous, it's not going to be differentiable there. It's not defined there, not differentiable. At x equals 0. It's an even function, so f of a should equal f of b. F of b is 2 squared plus 1 over 2 squared, 4 plus 1/4, 17/4. F of a is negative 2 squared plus 1 over negative 2 squared, 4 plus 1/4, 17/4. So f of b is equal to f of a, so that condition is satisfied. The continuity and differentiability are not, and the conclusion may or may not be true. So we're going to find out. So f of x is x squared plus x to the -2. So f prime of x, let that equal to 0. This is going to be 2x minus 2 x to the -3 equals 0. If we factor out the lowest power of x, we have 2 x to the -3, and that'll leave us with x to the 4th minus 1 equals 0. So it's 2 over x cubed times x to the 4th minus 1. And this first factor cannot be 0. So this one cannot be 0, but the second factor could be. If x to the 4th is equal to 1, that means x equal plus or minus 1. So the conclusion is satisfied, even though the hypotheses are not. So if the hypotheses are not satisfied, then the conclusion may or may not be satisfied. We've seen that in the last two examples. One example where it was, and one example where it wasn't. Okay, so here's a proof of Rolle's theorem. Extreme value theorem implies the continuous function f has an absolute maximum and an absolute minimum on AB. Let f of a equal f of b equal k, where k is a constant. Case 1, so assumption of Rolle's theorem was f of a is equal to f of b. So we're just making k to be that constant that's equal to f of a and f of b. So at the case 1, f of x equal k for all x and ab, then the derivative is 0, the derivative of the constant is 0. Case 2, f of x is greater than k. So there's three cases. Either f of x is equal to k for all x, or f of x is greater than k for at least 1x, or f of x is less than k for at least 1x. So if in the second case, the maximum is not an endpoint, and since f is differentiable, the critical number theorem implies that f prime of x is equal to 0 at the maximum. So that will be C, the point at the maximum. Case 3, f of x is less than k for at least some x in a, b, then the minimum is not an endpoint. And there, again, since f is differentiable, the critical number theorem implies that f prime x equals 0 at the minimum. So that point where it's equal to the minimum is going to be the point C. So that's the proof. And let's go on to the mean value theorem. The mean value theorem is a generalization of Rolle's theorem. Rolle's theorem, the slope of the line connecting f of a and f of b was horizontal, but this one is slanted, or it could be slanted, and so the theorem here is that there's at least one point C where the slope of the tangent line is the same as the slope of the secant line. So the tangent line is parallel to the secant line. The slope of the secant line is the difference of y value divided by the difference of x value, right? F of b minus f of a over b minus a. So there's and the slope of the tangent line is given by the derivative f prime of c. So there's at least one number c. If f is continuous and differentiable, then there's at least one number c, such that f prime of c is equal to f of b minus f of a over b minus a. So the slope of the secant line is also called the average rate of change. Okay, so I'll go over some examples and then the proof. First example, f of x equal minus x squared plus 4x plus 1 on the interval from minus 1 to 3. And we want to check whether it's continuous and differentiable, and it's a polynomial, so the answer is yes. Polynomials are continuous and differentiable everywhere. Okay, so f of b f of 3 minus 3 squared plus 4 times 3 plus 1, 4. F of a, f of minus 1 minus 1 squared plus 4 times minus 1 plus 1. That's negative 4. So we want to solve f prime of c is equal to f of b minus f of a over b minus a. So f prime of c is going to be minus 2c plus 4. Taking the derivative. It's going to be 4 minus a negative 4 over 3 minus negative 1. That's going to be 8 over 4, which is 2. So minus 2c plus 4 is equal to 2. Subtract 4 from both sides. We get minus 2c equals negative 2. Divide by negative 2. We get c is equal to 1. Yeah, the conclusion should be satisfied. Otherwise, we have something that we can publish and rock the make waves in the mathematical community. But yeah, if the hypotheses are satisfied, the conclusion has to be true. So there is a number c there that makes the slope of the tangent line parallel to the slope of the secant line, or same as the slope of the secant line. Okay, so second example, f of x equal x to 2/3 power. This is x to 2/3 power. Okay, so this is This is continuous, but it's not differentiable at 0. So the derivative f prime of x is equal to 2/3 x to the minus 1/3. That's 2 over 3 cube root of x. And that's not defined when x is 0, so not differentiable at x equals 0. So first, continuity is satisfied, but not differentiability. So the conclusion may or may not be true. So f of 8 is the cube root of 8 squared. Cube root of 64 is 4. F of -1, cube root of -1 squared, cube root of 1, which is 1. And we want to solve f of f prime of c is equal to f of b minus f of a over b minus a. So f prime of c is going to be 2 over 3 cube root of c equals 4 minus 1 over 8 minus a negative 1. So it's going to be 3 over 9, which is 1/3. So if we multiply both sides by 3 cube root of c, we get 2 is equal to 1/3 times 3 times cube root of c. 1/3 times 3 is 1. That cancels. And we have cube root of 3 cube root of c is equal to 2. Cube both sides, and we get 8 is equal to c. But that's not in the open interval. That's one of the endpoints, not in minus 1, 8. So the conclusion is not satisfied. We didn't find a number that was in the open interval with that slope. Okay, again, if the original hypotheses are not satisfied, then maybe the conclusion is satisfied, maybe it's not. Okay, another example. F of x equal x squared plus 1 over x squared. This is another even function. So this is x squared plus x to the minus 2. So this is not continuous at 0. It's undefined at 0. And if it's not continuous, it's also not differentiable at x equals 0. So these are not satisfied. And let's see if the conclusion is satisfied. F of 2 squared plus 1 over 2 squared, 4 plus 1/4, or 17/4. F of -1, -1 squared plus 1 over -1 squared. 1 plus 1 is 2. So we want to solve f prime of c equals f of b minus f of a over b minus a. F prime of c is going to be 2c minus 2 c to the minus 3. F of b is 17/4 minus f a is 2 over 2 minus -1. 17/4 minus 2 over 3. Divide by, distribute the denominator. We get 17/12 minus 2/3. Multiply top and bottom by 4. 17 minus 8 is 9/12, which reduces to 3/4. Okay, so I'll get another piece of paper here. So we have 2c minus 2c minus 3 equals 3/4. If we multiply by 4, we can get rid of the fraction there. We got 8c minus 8c to the minus 3 equals 3. Multiply everything by c to the 3. We get 8c to the 4th minus 8 is equal to 3 c to the 3rd. Bring everything over to one side. We have 8c to the 4th minus 3c to the 3rd minus 8 equals 0. Okay, so let's let g of c equal 8c to the 4th minus 3c cubed minus 8. This is going to be difficult to solve, but maybe we can just show that there is a solution. Let's say g of 0, 0 minus 8 is negative 8. G of 1, just plugging in numbers here, 8 minus 3 minus 8, negative 3. G of 2, 2 to the 4th is 16, 16 over 8 is 128, minus 24 minus 8, 96. So by the intermediate value theorem, here it's going from negative to positive. So by the intermediate value theorem, there has to be a solution between 1 and 2. So g of c equals 0 for some number between 1 and 2. And that's by the intermediate value theorem for continuous functions. G of c is a polynomial. So this one is difficult to solve, but the intermediate value theorem says there is some kind of solution there. So the conclusion actually is true in this case, even though the hypotheses were not satisfied. Okay, so go over a proof of the mean value theorem. The slope of the secant line is just the difference of y values divided by the difference of x values, f of b minus f of a over b minus a. So that means the equation of the tangent line, this is just a point slope form. It's the slope times x minus a plus f of a. And let's define y equal to that equation. Then let g of x equal f of x minus y. G of x is continuous because f of x is continuous. Y is just a linear function that's going to be continuous. Differentiable because f is differentiable and y is a linear function which is also differentiable. F of a, g of a is equal to f of a minus y, but if we put a y in here, if x is equal to a, y is just going to be f of a, so it's f of a minus f of a, which is 0. G of b will be f of b minus y, but if we replace x by b in the formula for y, the b minus a's cancel. We have f of b minus f of a plus f of a, which is equal to f of b. So g of b is equal to f of b minus f of b, which is 0. So by Rolle's theorem, there's a point c in the interval ab such that g prime of c is equal to 0. But the derivative, g prime of c, g of c is just f of c minus y, but if you take the derivative, you get f prime of, and y is linear, so it just f prime of c minus the slope of the line. So f prime of c minus the slope, and that's equal to 0, and solve for f prime of c, and you get f prime of c is equal to f of b minus f of a all over b minus a. So that concludes the proof of the mean value theorem. And then here's some corollaries. if f prime c is 0 on an interval, then f is constant on that interval. We had sort of the reverse theorem before, that the derivative of a constant is 0, and this is kind of reverses that. They say if the derivative is 0, then f is a constant. If f prime of x is equal to g prime of x on an interval, then f and g differ by a constant on that interval. If f is continuous on the closed interval and f prime is greater than 0 on the open interval, then f is increasing on the closed interval. And if f is continuous on the closed interval and f prime is less than 0 on the open interval, then f is decreasing on the closed interval. And that concludes this presentation.